So, how many people in this room, outside of the retouching class you may have done with me, have had any serious color theory? And I'm not talking about the emotional content of color theory, not that red means angry. Anybody?
I guess if you have Kelly Connell, she tried to do as much as possible.
Okay. As it regards to pigment or light, would you know? Light? Okay. But is Kate the only person in here who feels like has any sort of real experience that way? Okay, well then that's hopefully then a good sign that tonight won't go for naught. Okay. Oh, shoot. All right. So tonight we're going to start with a conversation about RGB and CMY. You'll see in parentheses K. We'll explain why that's in parentheses a little later on. These are both tristimulus colors of descriptions of color. Don't let the word tristimulus bother you. It simply means three stimuli, and again, red is a stimulus, green is a stimulus, blue, and on and on and on and on. The way this whole system comes about is it was actually all based on how your human vision really works. In your eyeballs, you actually have cells in your eyes that are sensitive only to blue light. You have cells in there that are only sensitive to red light, and cells that are only sensitive to green light. And science, early science, color science, understood this part, and they actually did experiments to prove that that actually is the case. You don't have cells in your eyes that are sensitive to every color in the world. What you have is cells in your eyes that are sensitive to primaries, and that then you can use those primaries, you can mix those primaries together in different amounts to achieve any color. So if you look at the experiment that they ran, there's a white screen right here. There's a shelf that comes out. There's a viewer on the other side that can only peer through a small hole in that masking screen right there. And what they can see is a target color that's down here at the bottom, this sort of lilac-y color that's shining on the wall. They see that bottom part, but this shelf prevents any of the light down here from actually contaminating the area up here. And then in the area up here, there are three different lights. There's a primary red, a primary green, and a primary blue, and they have rheostats on them. So, you know, rheostat is the thing that lets you turn lights up and down. It controls the intensity of the light. By using those three rheostats, this person can actually juggle things around, mixing different amounts of red, green, and blue to achieve this color. And indeed, when they did the experiment, it ended up working out that they realized that indeed you could pretty much create, and not pretty much, but exactly create any visible color that is made up of these RGB primaries. Does this make sense, this whole sort of little diagram? So the additive primaries, that's where we're going to start right here. And the additive and subtractive part of this matter because they are the vehicle, or the way the vehicle of color actually does work. So in the case of the additive primaries, they are red, green, and blue. In the case of also an additive color situation, cyan, magenta, and yellow are the secondaries. And what they mean by the secondaries is that they are not, so again, it's a tristimulus system. It's only got three primaries. However, if you mix those primaries, you can actually achieve the secondaries. So if you mix a pure red with a pure, so here, this is our red here, this is our blue here, and that's the green right there. If you mix red and blue together, you actually get magenta. If you mix red and green together, you get yellow. If you mix green and blue together, you get cyan. If you mix all three of these together, in the center, you get neutral gray. One of the keystones of what we deal with here in digital photography is the idea that equal amounts of RGB equal a neutral gray. That's how setting white point occurs. If you actually can find something in an image that should be neutral and you click on it with the white point setting control, either in Camera Raw, Lightroom, or Capture One, any of those, what it does is it takes whatever you've clicked on and it neutralizes it out so that it has equal amounts of RGB. That's how we actually do color correction in Photoshop. And it's based all on this. Now in this case, you'll notice right here in the middle here that it looks like this is a white. Well, white is a neutral color. All of this has to do with intensity. The idea of this is not, it will never change. We'll talk about that in just a second as well. So at any rate, it is an emissive system. It is an additive system. So if we take a look at this monitor right here, for instance, can everybody see this monitor right here? If you can't see it, stand up so that you can see it. This is as black as this monitor can get because it's turned off. However, is this as black as this monitor can get? So for the people who've been with me before, like Catherine, what's controlling how black this monitor? Don't you love that fact that I'm like rubbing my hands all over this? What controls how black this black can actually get? Say what? The lights. So what lights? The lights in the room. So the environments. I need everybody to keep looking at that monitor for me really quickly for 1 minute. Just hold on one more time. Monitor get lighter? Of course it does. It can't help it, right? So environment is what controls the black point in this whole system. Because you can't have anything darker than your monitor than when it's turned off. It simply can't get any darker than that. It doesn't have a negative whatever. This is just as dark as it can get. But you need to realize that your room actually does have an impact on this. Is the impact on the environment strictly the lights that you have on? No, it's what you wear. Right? So if I'm sitting in front of this monitor like this, and I've got a white shirt on, aren't I putting white on this monitor? Aren't I making that black lighter? Yeah, so that becomes a real problem when we try to deal with color in terms of shutting our system down. And all of these things become important to you in the field that you're actually going into. Not, for me, part of it is, clearly it's in many cases would be more important in terms of retouching than necessarily as an assistant or a digital tech. But it still matters in terms of that. I can't tell you the number of people who go into a studio. How many people in this room, when you shoot in the studio, your first thing is to calibrate your monitor? How many people do that? What the fuck are you looking at? You have no clue. And everybody makes judgments on what they're looking at. They all go, God, that's so bright, or God, that's so red, or whatever. And it's a guess. However, if you're also wearing a bright pink shirt and you're sitting in front of your monitor, you're throwing a bright pink cast on your monitor. So all of this has an impact, right? However, where I'd like to start with this, at least getting back to the whole color part of this, is that you start with something that is completely black. That's where this whole idea of additive system comes in. You start with nothing and you add. And what we add is energy. We add light. That's what's going to happen. When we turn these things on and you go to deal with color as far as it goes in this system, you're actually starting from black, which is no energy at all, and you start adding energy. And if you continue to add energy to the point that your RGB values are equal, which gives you a neutral gray, and you hit the maximum intensity of that, you will end up with white. So that's our extreme. Does that make sense to everybody? Now, who in this room knows or doesn't know? That's a better question here. Who in this room doesn't know that in the tonal range that we deal with in Adobe and Photoshop, whatever, we basically have a scale, a gray scale that starts from 0, which is black, to 255, which is white. Who in this room is not really comfortable with that idea? We're all good on that part, right? So again, that's what we're going to be talking about here. Not just about color in this situation, but also we've got to talk about the scale of going from black to white. Make sense? Okay. So we start with black, no light at all. We add proportional amounts of RGB to achieve any color, just like the little experiment we saw. Different proportions of it will achieve any color. Equal amounts of any RGB will equal a gray by definition. And again, white is equal at RGB, equal amounts of RGB at the maximum intensity. We've already talked about how black is. So the subtractive primaries, which in a sense are the negative of the additive primaries. In the case of subtractive primaries, it is CMY, cyan, magenta, and yellow. I'm going to leave K out for just a second. And again, in this case, cyan, magenta, and yellow are the primaries. You can think of these as ink on paper. So when we deal with these, you guys know from working in those printers out there, you never work with an RGB printer. There would be no reason to build an RGB printer there. I mean, theoretically you could do it, but it would be extremely difficult to do because the RGB primaries tend to fall in mid-tone ranges. So you wouldn't really have a problem making an RGB printer that could print midtones and darker, but you would have a really tough time trying to print really light detail. Unlike CMY, which actually has two primaries that are relatively light, cyan and yellow are actually relatively light, so being able to deal with primaries up in that end gives you a way to actually do the full gamut of it, as it were. So at any rate, we start with CMY, are the primaries in this case. The secondaries in this case, though, end up being RGB. So if you take cyan and yellow and mix those inks together, it gives you green. If you take magenta and yellow together and mix those inks together, they give you red. And if you take cyan and magenta together, mix those two together, those inks together, whatever, it gives you blue. If you mix all three of them together at their maximum intensities, in theory, you should get black, but you do not. And the reason you do not get black is because nobody has been able to come up with pure enough primary inks to this day. The biggest culprit in all of this is cyan. This is an extremely difficult. So when you talk about ink is not just this thing that Epson spits out that costs an absolute fortune. Do you know Epson ink is the most expensive liquid on earth? Yeah, don't get me on Epson. Then I'll start getting on Adobe, and then I'll just go right off the rails. And anyway, but at any rate, okay. So anyway, you don't get that because the reason you don't get black here is you get is because the impurity of inks. They can't find a substance that will give them a pure cyan. They do better with magenta and yellow, but they're still not perfect. So at any rate, when you mix these two together in the really light tones, what we call, so if we think about the tonal range, and everybody should know this part, when we think about the tonal range, the way most printers will talk about it is you will talk about highlights and shadows, both ends. You will talk about midtones in the middle, but then from the midtones to the highlights, you have what are called quarter tones, and if you have from midtones to the shadows, you have what are called three-quarter tones. From the midtones through the three-quarter into the shadows, the impurity of these inks really shows up. And instead of getting black, you end up getting this really shitty color brown. So to fix that, what printers do, both official printers, printing press people, whatever, but also Epson printers, Canon printers, what all those people, all those systems do is they start taking proportions of CMYK ink out, and they start putting in pure black ink, which is what K is. K stands for black. Now, the reason they don't use B for black is because B was already taken up by blue. So the word K actually comes from the word key. If you do any keying work in film or still life, either one, what keying work is basically, it's green screen work, it's chroma key work, or it's where you actually remove a background or you remove a particular color. Once you remove a particular color, the void left is black, and that's where the term key comes from, and that's where the K for CMYK comes from. You'll see K all over Photoshop, so now you'll know why. So anyway, this is all about absorption of ink on paper. So I ask everybody this. Can you guys turn around and see, there's a poster over here on the wall. It's got a little red strip on it and a little sort of cyanic blue strip on the bottom. Can everybody see that? There's another one right over there. The only one over there you can see is just got, all I can see of it is it's the emergency sticker thing about how to get out of this room or something, whatever. And it's got a little bit of red on the top. Can anybody tell me why those reds are red? And both of those posters, why do you see red? Jimmy.
They absorb every other color except that color.
That's exactly what happens. So the ink that we call red ink, what red ink does, really truly does, is that the lights that we have in this room, the lights that are actually shining on the wall, whatever, are essentially white lights. White light is made up of all the colors of the rainbow. All the colors that are visible exist in that white light. And that white light shines down, and the substance that we call red ink, what it does is it absorbs all the colors of that white light except for red. And the red gets reflected back, and that's what hits all the sensors in our eyes that are sensitive to red, and that's why we see red. Does that sort of make sense? So, but what you've got to remember is the whole trick to this is that what's happening, the reason we see color and the reason we see any of that stuff, whatever, is that light is being subtracted from the equation, right? That white light, what's bouncing off of that, what's bouncing off the white wall is the majority of the white light. But what's bouncing off that red stuff right there, it's missing. It's got the red component in it, But what it's missing are all the opposites over here. It has no cyan in it. All the cyan got absorbed by it. And varying amounts of magenta and yellow have also been absorbed in it. And that's where the whole subtractive thing comes from. So in this case, we start, it's just the opposite of our additive system. We're now starting with white. We're starting with it as bright as it can be, and you're adding a substance on here now to subtract light. Does that make sense to everybody? We good on that part? Okay, you can subtract, again, the same system works out in the RGB case here, is that you can use varying amounts of these three primaries of the cyan, magenta, and yellow to create any other color. However, in this case, equal amounts of CMYK do not equal gray, which is a huge problem for color scientists, for people like us. How many people in this room edit their work in CMY? Nobody does. It is extremely difficult to do because of this inequality situation, the fact that you've got a highly deficient cyan and a slightly less efficient magenta and yellow. So black, again, does it equal the CMY at its maximum intensity? Theoretically, yes, but in reality, no. So how white can white possibly be? How white is white?
0.
Say what? 0. 255 in Photoshop, but in practical terms, practically speaking, what's the whitest thing you can have in a subtractive system? The piece of paper. It doesn't get any whiter than this. There's no ink on it. The minute you start adding ink to it, we start subtracting light. So at its beginning, the whitest that you can actually get is the piece of paper. All right, we are going to blow through this. I need everybody to get on a computer really quick and open up Photoshop for me really fast. You've all said that you understand that part, but I just need to make sure that everybody is understanding that part. We're also going to get into some terms today that some people find difficult to remember the idea behind them. So it's a place that I'm going to take you that you, if for instance, all of a sudden you say to yourself, you know, I'm really kind of unclear about what saturation really is. It's a way to, it's a source, a place for you to go to actually find that out. So with Photoshop open, if you click on the foreground color, it's the little color swatches that are sitting right down on the lower left-hand side. It doesn't matter what one is on the front, just click on it to actually open it up. And what you will actually see is the color picker will come up. Now, in the case of me, I've actually got a black in here. That's why I'm at RGB values are 0, 0, 0. So I'm going to ask you right now to get the same place that I am. Go ahead and zero out your RGB values. If you click and drag across the R value, you can type in 0. If you hit your tab key, it will take you down to the next little square. Hit 0 again, tab key one more time will take you down to the blue. Type in a 0 there as well. You should end up with a black just like I have. If you then click on the R value and type in 255, that is the maximum red you can get. This is by definition a pure red. It is on our scale of 0 to 255, this not only exists tonally, but this also exists in color. We have 256 possible reds, 256 possible greens, 256 possible blues. To see what those truly look like, if you click on the R slider, the little radio button next to R, this shows you the possible reds that you actually have on that scale from 0 to 255. So if you click on these little arrows at the top and you drag them all the way down, you can actually get a visual idea of the entire scale as it's going along here. So if you crank it all the way down to the bottom, you have a 0 red. That actually is a real thing in Photoshop. 0, it is a value, even though you would say, well, that's ridiculous. That means there's 3 blacks in Photoshop, and there are. There's a black red, there is a black green, and a black blue. And the reason that exists is for math, for lack of a better way of putting it. But at any rate, if you click on that little radio button, the column, no matter what radio button you click on, that's what this column becomes. So for instance, if you click on green, you'll actually see this is the green scale that exists right here. The reason it's zeroed out down at the bottom is because I have 0 green in here. If you were to click and drag it all the way up, you'll see that your green goes all the way up to 255. But I'm going to go back to the red one for just 1 second. Click on that radio button. And again, drag it up and down. You can see that this is the way Photoshop and all digital cameras, everybody, whatever, deals with this whole idea of color. So we are dealing, again, so it's from 0 up to 255. The same thing will happen with green. Same thing will actually happen in blue as well. I am going to go ahead and put in 255 for my red. I'm going to hit the tab key and put in my 255 for my green. And what you'll see here now is you've actually got yellow. Again, what this is a consequence of, we talked about this already before. If you mix equal amounts of red and green at their maximum intensity, which is what this is, you end up with yellow. So if we go back and we look at our additive color system, this is exactly what we would expect right here. This is showing you that equal amounts of red at their maximum intensity, pure red and pure green together, actually equal this yellow. If we zip back out and you actually change the red to 0, hit 2 tab keys so that you go down to the blue and put in 255 for the blue, we end up with cyan, which is exactly what we would expect. We're mixing the maximum amounts of green and blue. Again, if we look back at our little color chart right here, again, the maximum amounts of green and blue together equal that cyan that's sitting right there in the middle. If we go back to the Photoshop again and we add 255 for the red so that you have 255 for all three of these, you end up with white, which is exactly what we would predict given the little chart that we just looked at right here. That is so equal amounts at the maximum intensity of red, green, and blue together equal this white that's right in the middle. Is everybody good on this part? Or any questions about this? Okay. So this is what we talk about in terms of tri-stimulus. You can see that we are actually able to create all the colors of the spectrum can be described in the term of 3 different stimuli. In the one case, it's either RGB. In the other case, again, theoretically, the CMY part. K is picking up the deficient part of it, but we're still basically dealing with that notion of 3 stimuli. So human eyes are tri-stimulus. This whole system is based on how your eyes work. However, and this is a big however here, it does not have to be 3 primaries. So the way we describe color does not have to actually function only as an RGB system or a CMYK system. However, it does need to have 3 axes to it, and we'll see what that can actually, what that means in just a second. It can be plotted in 3 dimension, and it actually is plotted in 3 dimension. We're going to take a look at what that looks like right here. So this is an imaginary cube. I realize that this is a 2-dimensional illustration of a 3-dimensional object, but work with me on this one, okay? So in this case, what I need everybody to do is try to imagine this room as being a cube. So let's forget this half of the room here, and let's forget this half up here. Let's just imagine that this is a cube right over here. Does this make sense to what we're talking about here? So everybody can, so what I'm trying to get you to do is visualize what that thing is in real space. So ignore all of that other half. So just realize that the room, however high it goes, is however deep it goes, and however how far it goes. Does that make sense, everybody? We good on that? Okay, so if you take a look at the way this illustration works, what it's got is, you can imagine the corner back here. Here, I'll even add a fake wall. If you imagine this corner right down here at the very, very, very bottom, that's where black lives. You have 0 green, 0 blue, and 0 red. However, if you look at the axis here for green, it's actually going up to the ceiling. So what I'm going to do is, I'm going to stay right down here on the floor, 0, 0, 0, all black. However, then I'm going to take a line and I'm going to go straight up to the ceiling that's right in this corner. It doesn't go into this part of the room at all. It doesn't go into this part of the room at all. It simply goes straight up. And at the very top up there, I have 255G. That's exactly what you guys just did on your little scale in Photoshop. So do me a favor, go back to Photoshop really quickly. Open up the color picker. Click in your red space, put in a 0. Click in your green space, put in 255. Click on your blue space and put in 0. And what you'll have, you click on the radio button for G. And what you will see is exactly what happens in the line that goes from the floor here straight up to the ceiling, as long as you do not go out in the room this way or out this way. Does that make sense? We good on that part? Okay, so the red axis for this is actually this direction in the room. So I'm going to go back down here to black, 0, 0, 0. If I start here and I go along the line on the floor right here, all the way out to the end, to the edge of the room right here, I never come up at all, so I have no green. I never come out this way at all, so I have no blue. I hit this point right out here. This is where my red 255 is. So again, if you click on your little color picker in Photoshop, click on the red radio button, put in 255R, hit the tab key 0 green, tab key 0 blue. The column that you were looking at is exactly what the line that runs along the floor from the corner, which is black out here to the edge, which is green. Which is pure red. Does this make sense, everybody? So then zero your color out one last time. Put zeros into all of them. Click on the blue radio button. Put in 255 for the blue. And that's actually what happens if we start here in the corner and we run along this wall edge right down here. So I'm completely down on the floor. So I'm not up in the air at all, so I have no green. I'm not out in the room at all, so I have no red. But this is where pure blue actually exists out here. Does that make sense? So if I then think about doing all of these at their maximum, I'm doing all of the blue all the way out, pure blue. I'm doing all of the red all the way out here, pure red, and then all the way up to the ceiling. So I'm in the opposite corner up here. This is where I am. All 3 primaries at their maximum color up here. What is the color of this corner right up here? White. Does that make sense to everybody? What's right here in the middle of the room? I'm halfway up, halfway, I'm halfway up, halfway out, and halfway this way. Middle gray. That's exactly what it is. Within this cube, every color possible exists. It's just that they exist in different places. So white's up here, middle gray's right here, sort of, again, different color. Well, we'll see here in just a second because I've got a better illustration of it. So does this make sense? The advantage of a system like this is that instead of trying to talk about color as color, greenish blue, what color is that? Nobody knows. However, in a color system like this, I can specify a location. I can say this point in this world, and if you go there, the color will always be the same, and it'll be the same for everybody. So I get away from this sort of like non-descriptive version of color to something that's extremely precise and exact. And it's precise and exact because of location, not because, again, kind of like, oh yeah, it's like a mauve. Can anybody here tell me what mauve is? Yeah, therein lies the problem. So at any rate, it is 3-dimensional, and that's a key part for this. It is a 3-dimensional space. There's a unique point for each and every color. You can describe, this can be an RGB world, which is what we're looking at right now. It can also be a CMY world. However, it does not have to be either one of those. You can use HSB to describe this 3-dimensional space. How many people in this room have no idea what HSB means? Oh, I love that. Okay. How many people in this room know what HSB is? So what is it? Hue, saturation, and brightness. So we're going to talk about exactly what hue, saturation, and brightness are in just one second. Okay, so but the key to this is, again, you can describe color now in terms of its location. And that's what Photoshop does. When it gives you these RGB values, these are actually telling you there's this place in this world, and there's a color that lives at that place, and that these describe the coordinates of how to get there. This is like the GPS of color. So it just tells you where it is. So if we look at this example right here as an example, again, these are all on a scale of 0 to 255. So this is a red of 51. So a red of 51 is not a very heavy red, right? On the scale of 0 to 255, it's about 1/5 of the way in. And if you can take a look, the red axis, again, is starting from this edge of the room and moving in this direction. You can see we're not too far out into this direction. This is where this piece of color is right here inside the cutout of this world. Pure red would be all the way over on this edge over here, so it's not very, very much red. In terms of the green right here, this 153, it's sort of in the middle, and you can see, again, the green axis is going from the floor up to the ceiling, and that puts the location about in the middle of this cube, so it's about halfway up. That's about right. And then the blue, it's actually a pretty intense blue. It's a pretty heavy blue. So you can see in the blue axis where we're coming out from that back wall, we're coming out, we're not all the way out at the very edge here. That would be a 255, but we're getting pretty close, and that's where the 204 comes from. So this whole system right here is describing color by location, which is how we need to actually deal with it. I need everybody to go into their Finder really quickly. Go to your application folder for me, please. If you scroll down to the bottom of your application folder, there is a utilities folder in here. I want you to click on that to open it up. With the utilities folder open, there is a color sync utility. It's this guy right here. If you double click on it right off the bat, you may not see what I'm hoping for you to see, so just hold on if that happens. There's a series of icons that run across the very top, 5 icons that run across the top. I want you to click on the second icon. Don't click on Profile First Aid. That's usually what's on when it opens up. But Profile's the one that's actually next to this. When you do that, you should have a screen that looks something like mine. I tend to have a whole lot more profiles than most people, so this may not look exactly the same as yours. But at the very least, you should have something at the top that says System. Does anybody not have this? Okay, I want you to open up the System part, and then I want you to click on Adobe RGB 1998. And you'll see a display that comes out on your screen. And if you click on this, you can actually move it around. This is the three-dimensional color space that Adobe RGB actually occupies. So tonight when you go home, you can get all fucked up and you can just open this up and spend hours doing this. It's better than a lava lamp, trust me. No. Does everybody get some idea of what's going on here, right? So remember when we were talking about in our the previous part that we were just looking at here, if we're looking at this world right here, this is a different version. It is a three-dimensional world, but it's not an RGB world. This one is actually based on HSB. That's what's going on here. So we're going to talk about HSB in just one second, and then I'm going to actually show you how it relates to this guy. But what I wanted everybody to realize here is that how many people in this room at least are familiar enough with working in Photoshop that most of you guys are working either in Adobe RGB, ProPhoto RGB, or sRGB. Is that true of everybody in this room? Is there anybody in this room who has no idea what I am talking about when I say those three things? Okay, you may not know why you're using one, but you know that you actually are using one. We're going to get to all of that in color tonight, okay? So at any rate, that's what's going on here. Three-dimensional space. It has got to be three-dimensional as far as that part goes, and I'm going to show you why in just one second. Okay. So, who in this room can tell me what hue really is? Well, first off, let me ask you this. For those people who weren't familiar exactly or couldn't necessarily tell me hue, saturation, brightness, is everybody in here at least has heard that term? Hue, saturation, brightness. Or in some cases, it's hue, saturation, lightness. Those are pretty interchangeable. There's some technical differences between the two, but not enough to worry about as far as this part goes. But you've all sort of like heard of that part, right? And instinctively, I think everybody sort of says, well, I kind of know what that all is, right? So when I say to you, what is hue? What is hue? See, and this becomes the problem, is that I've got a room full of photography students who should be knee-deep in color theory right now and understand exactly what this is, be able to write the book on it. And it's an instinctive thing that you think you know, but trying to articulate that becomes extremely tough to do. And so that's something we need to get away from, okay? So hue is primarily what we call, it's the property of color that distinguishes it from other pure colors. So when we talk about red, you have, the minute I say red, you have this image in your mind of what red is, and that's distinguished from green and blue or purple, or it's distinguished from all those other colors. It's that property. That is what it is when we are talking about hue. It is the thing that makes those distinctions, and you don't need to worry about that part of the definition. So I need everybody back in Photoshop with the color picker again. So you remember I said if you don't know something, that this color picker can actually help give you the answers to that if you don't really remember what things necessarily are. So I need everybody to pick a pure red again for me. So if you can tap on the red part and type in 255, hit the tab key, put in 0 green, tab key 0 blue. We've got a pure red in our new little patch up here. If you look at the 3 boxes that are sitting at the very top here, these 3 boxes are hue, saturation, and brightness. That's what these 3 things are right here, this HSB. If you click on hue, remember every time you click on a radio button, what gets shown to you in the column is the radio button. So this is the entire gamut of possible hues that we've got here. So again, if you click on the color slider on the little triangles at the bottom and you start to run through these, you can see this is the entire range of hues that we've got. You'll notice that we start at red, we go all the way up, and we actually end at red. This actually ends up being a circular thing, and we will talk about that in just a second. But this is the reason I keep pointing this out is that, so 6 months from now, if all of a sudden you're struggling with, God, not sure, do I really want to be changing hue or saturation on this, whatever, if you are looking for the definition of it, you can come to this place. You can click on one of those radio buttons, and then the column becomes what it is you have clicked on, and you can actually start to play with it, slide through it, and it will then hopefully make sense to you guys what it is. So in looking at this, has anybody got any doubt at all about what hue is? You've all got that part, right? Okay, great. Saturation. Who in this room can tell me what saturation is? Oh, wait, 1 second. Sorry, just let me go back really quick. One. In the case of this, the 7 little dots at the bottom, they all have the exact same saturation. They all have the exact same brightness, but they all have a different hue. That's what's going on here. So, saturation. What is saturation?
It's like where it is on a scale from white to 255.
So, Catherine's saying it's a scale of from white to 255.
Of like 255 of a certain color. You know what I'm saying?
No,
like
I have no idea what you're saying.
Like a fully saturated color. So like if you go on to, if you click the saturation radio button, it starts as white and then goes to 255 red. And that is the range of
yeah, but that's also a little misleading because brightness is also playing a role in this. Let's take this for a little bit simpler point of view. How many people in this color have ever turned an image that was a color image into a black and white one by desaturating it? Well, let's just do that. I need everybody in Photoshop really quick. Do me a favor. Can you guys get online to the server? To get online to the server, how many people in here are on their own laptops? Okay, so if you're on your own laptop, click on the Go button in the Finder. Come down to Connect to Server. And you want to type this in right here, which is, this is the server address you want to type in, lowercase AFP://172.20.208.221 and say connect. Did that connect you to a dialog box that opens up and says class projects? Go to class projects. For everybody else, there is, if you go to the dock at the bottom of this computer screen right here, go all the way down to the dock. There is a little cube in that dock it's a white cube with a blue apple on top of it. Does everybody see that? Click on that. If you do, again, another dialog box will open up. You want to click on class projects. And then let me connect to mine. Once you get into class project, you will need to navigate to my name, Engelhard, with an E. Inside of Engelhard with an E, there should be a thing that says, let's see if we can do it with this guy here really quick. No, let's not do it with that. There should be a folder in there that says assignments complete. Does everybody see that? Inside assignments complete, click on student files for week 1. And then click on student files for week 2. Inside week 2, you will actually have, there's a folder that says 201003227_VER. Do you guys see that? Oh, I got a better one. I got a better one because we're going to use this one later on anyway. Go to the one that says DNG Custom Profile Examples. Does everybody see that? Do we have that? Then inside the folder that says 2010917_, you see that guy? If you keep going all the way over, son of a bitch, that is not what I'm looking for. Sorry. somebody screwed this up. Okay, this is an assignment file for my retouching class, and somebody has put their assignment in this folder. You can take them to water, but you can't. Okay, does everybody see the Bruce Frazier 20 copyright 2015? Does everybody see that? Yeah, double click on it. It'll bring it up into Photoshop. If your color picker is still open, you need to cancel out of that, and you may have to double click to do that. Oh, looks like mine's going to continue to go. It'll bring you open into Camera Raw. I don't care what this thing looks like. You can just go ahead and open. If it says open object down there at the bottom like mine does, hold down your shift key so that it says open image. Otherwise, just click on open image. And we should have this thing that looks like a castle inside of Photoshop. Everybody got that one? Okay, we're going to, wow, this is such a long way to get to saturation. I need everybody to go up to the image menu, down to adjustments, down to desaturate. And you have a black and white image. And the reason you have a black and white image is that what saturation is it's the purity of the color. That's what it is. So at one extreme, you have the purest the color can be. So the most pure, intense red, the most pure, intense green, or blue, or pink, or whatever. The most intense it can be. And the opposite end of that is gray, where you have no color at all. Does that make sense, everybody? That's what saturation is. So again, if you're in Photoshop, click on your little color picker right here. I've still got my 255 for my red, 0 green, 0 blue. I've got my little bars all the way up to the top, and right now my radio button is B. I'm going to ask you to click on S for saturation. So if you click on S, this is what Catherine was actually talking about. On the one extreme, you've actually got this the most intense red that you can possibly have. If you click and you drag this down on the other end, whatever, it ends up being white. And a lot of people say, well, white, that doesn't make any sense at all. But the truth of it is, white is a gray. It is void of color. There is no color in white. However, what most people would expect would this to be actually middle gray or some middle-ish tone of gray. The reason this thing is so bright is because our brightness is still set at 100%. If you click on the brightness slider and drag it halfway down, you end up with your middle gray. But the point being is that saturation, again, is from the purest color possible to to a gray. That's the difference. Okay? We good on this part? Okay, let me get back to the lecture really quick. We're going to blow through this as fast as we can, guys, because I know lecture just isn't fun. So at any rate, brightness. Now this is the one that most people have this is the one people struggle with the most, I think. It's the hardest concept to really grab. So the way to think about it is it's the property of a color by which it appears to contain more or less light. Make sense? So at the one extreme, you've got black. At the other extreme, you've actually got white. And the differences in between are those different shades. So if you look at the 7 patches that are on the bottom down here, they are all the same hue. They are all the same saturation. The only difference in these is brightness. And again, if we go back into Photoshop and we can... For our hue, you can leave the hue here at 0 for the saturation. I want you to click the saturation and crank that all the way up to 100%. And then click on the brightness slider and take it all the way up to 100% as well. So you should have HSB values of 0, 100, and 100. With the radio button on brightness, that'll show you the brightness slider. Now if you click on this and drag it up and down, you will actually see it is the scale from what we would call the lightest of this color, the lightest of the reds, down to the darkest of the reds. If we put in 255 for all of the RGB values, so go ahead and add 255 for the red, 255 for the green, and 255 for the blue, we end up with a white. However, if you've got the radio button still on brightness, you will see the brightness scale goes indeed from white through middle gray down to black. Are we good on this? Okay. So, how many of you painted a color wheel when you were in grade school? All of us did, right? The problem with the color wheel that you painted in grade school is it's based on pigment, which is actually a subtractive primary system. It doesn't work like light does at all. So this is a color wheel based on light. So the way this starts out by definition, and this is the way it is, the international standards community has always set it up this way. So you'll see other people who don't really know what they're doing with it turn slightly. They'll, like red will be at the top, or red will be on the left-hand side instead of the right-hand side. But anyway, this is the official version of it, the way it's accepted. And you'll see right here, circle. How many degrees in a circle? 360, right? So if I'm standing right here and I go all the way around, didn't I just do a 360? If I go only halfway, did I do a 180? Okay, so you guys, come on. All of us are, you remember when you were in high school, drinking after the game, doing 360s in the parking lot when it was snowing? No, nobody remembers that. I don't remember that, and I'm more likely to have done it than probably more. Anyway, so hue is determined by angle, the angle that goes around this. So when we look at this color wheel right here, by definition, red is always 0. It also makes it 360 as well. Again, if we go all the way around, we get back to 360. That is the definition of red. In the construction of the color wheel, because RGBs are the primaries, they make them as far apart from one another as they can possibly be. So because we have 360 degrees and 3 primaries, they simply divide 3 into 360, and you get 120. So green is 120 degrees away from red. Blue is 120 degrees away from red as well. And then green is 120 degrees away from blue. Does that make sense? They're as far away from each other as they can be. Where these things two mix is exactly what we were talking about earlier. If you mix green and red together, you get yellow. If you mix green and blue together, you get cyan. And if you mix blue and red together, you get magenta. Does this make sense to everybody? So again, I've got my 3 primaries, my additive primaries, and I've got the inner parts, my secondaries. Are we good on this? Okay. So hue is around the outside of this. The opposite, if we go straight across this color wheel, we end up with a complementary color. What is a complementary color? Say what? It's not essentially, it's exactly the opposite. So Catherine's right on the money. It is exactly the opposite. The opposite of red is cyan. The opposite of green is magenta. The opposite of blue is yellow. And vice versa. The opposite of blue is yellow. Yellow is blue. Does that make sense? This is how we deal with saturation. If you mix the complementary color into a pure color, you reduce its saturation because it is opposite on the color wheel. If you do it in perfectly equal amounts, in the very center right here, we end up with neutral gray, no matter which ones you mix. So if you add equal amounts of red and cyan, you wind up here. Equal amounts of green and magenta, you end up here. Equal amounts of blue and yellow, you end up here. Equal amounts of whatever the hell this color is and whatever the hell that color is directly across from it, you end up in the middle right here. Does that make sense to everybody? So that gives you hue is the edge around here. Saturation is the distance from the center out. So the very edge right out here, this is where pure red is. That's not pure red right there. We're starting to desaturate. By the time I get down to here, we're completely desaturated. Does that make sense? We good on this? So again, all of this matters in terms of space, where this stuff is. So the most pure colors are on the very edges. The most desaturated colors are right in the middle. The hue is around the outside of here. What's missing from this? This is a 2-dimensional model. It's not 3-dimensional. What's missing? Brightness. I have no white here. I've got a neutral gray right here. I have no black in here either. That's missing. I can't have those in a 2-dimensional model like this. I've got to go to 3 dimensions to actually get that. So we've already gone through what all those are. The way they actually come up with it is they take the color wheel and they flip it so that it's like a disc. So that it's like, I said this to somebody else the other day, so it's like an LP on your stereo playing. And they're like, what's that? It's like CD maybe? No, anyway, do you guys get where the illustration right here? So again, I've got the same thing. Hue is going around this. So I think of this as like the equator of the Earth. That's the way I tend to think of it, right? If the Earth is not tilted. So at any rate, hue is going around the outside. Saturation starts at the very center of the Earth and moves out to the very edges. But then we add the third dimension, brightness. And as you start to go from the middle of the Earth up to the very top to the North Pole, right here, you go to white. And if you go down to the South Pole, you go to black. Does that make sense what's going on here? Why is this a double cone and not a cylinder? Why isn't it like a can? Because as you get lighter, you lose saturation. As we start going from here up towards white, we're getting lighter and lighter and lighter. The lighter your colors are, the less they're able to be saturated. So the area down here around the center of the equator where we've got middle gray is right here in the middle. We get our most saturated colors as we start to get lighter and lighter and lighter and lighter. Eventually, we go to white, which is no saturation at all. Same thing happens as we move to black. As you start to get darker and darker and darker, this range of saturation starts to get narrower and narrower and narrower to the point that when you reach black at the very bottom, you have no saturation at all. There is no color in black. Does that make sense to everyone? We good on this? So HSB is the way all color works in a digital world. This is everything that we are talking about exists right here. So again, I need everybody to go to their, we don't need to go to the color picker because we've already gone through all of this. We're so ahead of ourselves, guys. This is going to be great. I need you to go back to the color sync utility for me, though, really quickly. So in the color sync utility, in the sort of Adobe RGB thing that we've got up, this is how these worlds are created. If you take a look and you orient this the way it's supposed to be correctly, you'll have white at the very top. That's what those little white X's are about. Black is at the very bottom. That's what those little X's are about. If you tip it on its side, you can see the area that goes right around this edges, right around here. This is actually the hue at its most saturated part. And if you could see in the very middle of this, we go from white to black down in the very center. In the very middle of this world, just like we did in the middle of our cube room. Remember we said in the middle of this cube room, we would actually have a middle gray. That's where the gray is that it runs from the very top right here down through the center of the Earth, North Pole down to the South Pole. That's where our grays are. Does this make sense? Okay, so I'm going to keep on going on. I'll come back to this in just 1 second. Okay, one last thing we need to talk about. I'm not going to jump that far ahead. I'm going to go right here. Is this. So the reason I bring all of this up today is how many people in this room have got their color down pat? How many people in this room struggle with exposure? No one. You all have perfect exposure all the time. I do. All the time. I haven't had anything less than perfect exposure in 15 years. How many people in this room would like that? How many people in this room have perfectly predictable color all the time, 100% of the time? I do. How many people in this room would like that? How many problems would it solve for you if you had perfect exposure and perfectly predictable color? Quite a few, right? Let's sweeten the pot. How many people in this room, when you go to print something out, you're looking at your screen, you print something out, it looks a little too red, so you put a curve on your image in Photoshop, you suck a little bit of the red out, you do another print, you bring it in this room, you put it up on the fucking board, and you go, well, now it's got a little too much green in it, so you go back in, you put another curve on there, you suck a little of the green out of it, you do another print, and you come back in here, and you take a look at it, you say, well, now it's got a little too much pink in it, so you go back and you take out a little bit of the red and the blue. How many people work like that? Okay, let me rephrase that question. How many people get an image on their screen and print it out and it's perfect? I do. How many people in this room would like to have that? Exactly. So that's what this is all about. So even though we've spent an hour now talking about shit that you think you really don't care about, you really do care about this. And ultimately what it's going to lead to is this. And what this is a color managed workflow. So we have got to talk about the nature of a little bit of our devices here, because this becomes the real problem issue that we've got in all of this. Everybody's eyes in the world, whatever, they're tri-stimulus, we've already talked about that, whatever, but they are considered device dependent. And what that means is that they see color slightly different than all the other eyes in the world. So if you put a color swatch up on that board and everybody in this room turns around and looks at it, all of us see that color in a slightly different way. Device dependence. If we actually put a color up on a computer screen right now and we were to all turn all the computer screens so that they all faced the back wall, and then we all stood on the back wall and looked at it and they were all showing the exact same color, do you think all the monitors would look identical? Not a chance. They would all be not radically, but they would all be different. Device dependence. If we take a file and you print it on one printer here, you print it on an Epson, and then you print it on a different Epson or another Canon or something like that, are the prints going to be identical? No, there's always going to be variation in that. Again, device dependence. Well, how about your cameras? If I took my Canon camera and you took your Sony camera and you took a picture of a red ball, I keep using red. Let's do another color. I took a picture of a turquoise ball. Would all those cameras give us the exact same color? No, because they are all device dependent. Every device that's out there has a dependency. It is a slightly unique, slightly different interpretation of color. And the problem that we have in dealing with color or trying to come up with consistent color is are those dependencies, are those slightly different discrepancies between color. Does that start to make sense, everybody? So we need to talk about a way to actually fix that part. And so I'm going to undo this. You don't really see this on the video, but you will hear this. You're not going to see it on the screen because I'm going to take this back here. I need to show you guys something on this whiteboard, so this way you can still hear the video, but you won't actually see what's going on, but you will remember it. So I'm going to do a small illustration here of device dependence as it relates to a monitor. So tonight what we're going to try to do is get through how to standardize color for everything that you've actually got. I'm going to start with the monitor part right here, just so that you guys have some. It's the easiest way to describe it. It's just the easiest way to do it. So I've got a file, and my file's got a color in it that is a red of a 250. Sorry, I keep putting these dashes in here, and they look like minuses. So I've got a red. Wouldn't it be funny if I did these all color-coded? Like the red was always in red, and the green was always, yeah, that's a time killer. Okay, I've got a red of 250. I've got a green of 160, and I've got a blue of 40. Does that make sense? And it's just some color. As a matter of fact, you can go into Photoshop right now. Everybody go into Photoshop really quickly because I want to see what color this is. And in the red value, type in 250 for the red, hit the tab key, go to green, type in 160, and then for the blue, go in and put in 40. And you end up with kind of like a sort of an orangey color. Okay, so anyway, that's the color, right? So when I look at this on a monitor, though, shit, I gotta find something in here. Okay, you really want to know what a good assistant or a good digital tech would do? They would have brought their own. Now, if this doesn't work, I am going to like, no. If this doesn't work, you guys will cut me some slack, I hope. Okay, I've got a monitor now. All right, so this is my file color. My monitor, though, again, the device dependence on my monitor, it doesn't show me what my file's asking for. It shows me a different color. And let's say, I'm just going to come up with numbers. So let's say it gives me a red of 245, it gives me a green of 190, and it gives me a blue of 15. That's device dependence. A different monitor would give me a different set of values here. And another monitor would give me another set of values right here. That's why I cannot get predictable color. This is why color becomes a real challenge for us. However, thanks to Apple in large measure, but really the ICC, International Color Consortium, they came up with a system to fix this. And the system to fix this is profiles. What a profile is it's something that's actually created. We're going to create them tonight. It's created to measure the device dependence, the drift. It measures the discrepancy between what was being asked for and what's being given. Does that make sense? So what the profile does here, and the way you do profiles, the way you make profiles is that it's a software-hardware combination. The software kicks out colors, known colors. The hardware part measures those colors, and wherever the discrepancy is what the profile then needs to fix. Does that make sense? So we're going to do that today for pretty much our whole system, I hope. So the profile, P-R-O-F-I-L-E, the profile does that whole thing, and the profile realizes that when the file calls for 250, that the monitor shows at 245. So it understands that there is a deficiency here of 5 red. So to fix my image, it knows that it needs to be an additional 5 red when that value is called for. Does that make sense? So it's calling for 250. The monitor's showing at 245. The profile says, well, okay, when that thing's calling for 250, I know it's given at 245, so I've got to add 5 points of red to fix that device dependency. Does this make sense? Same thing happens in the green. It knows that it's giving that the monitor is showing too much green, so for the green, it's going to subtract 30 green. And then finally for the blue, it knows that it's very deficient in the blue, that it's 25 points deficient in the blue, so it knows that the blue needs to be a plus 25. Does this make sense to everyone? And then finally, if you use the profile on this monitor, so this is the monitor plus profile, you end up with a red of 250, a green of 160, and a blue of 40. Does that make sense? So that this right here, this monitor plus profile, equals what the file actually called for. Every single monitor has got its own unique profile. You can't do this work on one and put it on another monitor. It doesn't work that way. Every monitor is completely unique. This same system is what we're going to use for printers, but it's also what we're going to use for our cameras. Are we good on this part? So if we go back, are there any questions about this part? Because if you get this part, you'll get why we're here tonight. Okay, so there's a couple other last things that we need to talk about in the system, and then we're actually going to start to make some profiles. I'm going to show you the printer one first, just because I've got this stuff here, and we lose it at 8 o'clock. Then we're going to look at the other two here. I'm going to do a monitor profile for you as well, and then you guys are actually going to do camera profiles. So here's the holy grail of it all, if we can do this. So we have got, how many people in here are shooting film? Is there anyone shooting film? Okay, so you guys, you can do this in shooting a film context as well. If you're shooting negative film, it pretty much doesn't matter because you've got to assign color. But you can do the same sort of setup with a scanner or with a camera. So if you're doing film and you're actually scanning your film, or if you're doing prints or scanning, flat art, that kind of stuff, whatever, you can still do this very same system. So, but here's the trick. Every single scanner and every single camera has got its own unique interpretation of color, and we need to eliminate that device dependence. We need to do this same sort of system so that the color that comes into our software has been de-deviced. Does that make sense? I've gotten rid of the device dependence. It is the color it is supposed to be. Are we good on that part? And no matter whose camera is shooting that, if they have their own profile, the color that is then coming into this software from two completely different cameras will be the same because we eliminated that device dependence. Good on that? So at any rate, so we're going to build a profile for your camera to take care of that stuff. When we get into here, this is actually camera raw right here. So this is where that we would actually bring this in to then bring it into Photoshop. Does that make sense, the little trail that I'm doing here? Okay, so this input software right here, this is where you assign those profiles. This is where you actually apply the profile that you've made. So your camera, information is coming in from your camera, the profile gets applied in here, and then we bring it into Photoshop. And in Photoshop, this is a very special place, and we need to talk about this. So in Photoshop, these are working spaces in Photoshop, and they have a very special place because the places that are inside of Photoshop are mathematical. They are not device dependent. And the reason that matters to us is this is the place where we can exchange that color information. It is the neutral place. So I have a camera, I have a picture, and I bring it into here, and it goes through the whole profiling system. So I reach it into Adobe Photoshop right here, and it indeed is no longer device dependent. But then let's say I give a copy of it to Jimmy, and he opens it up on his computer. Well, he's got a mathematical space that's identical to mine, so when he opens that file up in Photoshop, it's identical as far as Photoshop goes. Now, his monitor is a different issue, but as far as Photoshop goes, it is the exact same color. There has been no shift in color by trading these files around. Does that make sense? Because these spaces are identical for everybody because they are theoretical. They are spaces that were built based on math that exist inside of Photoshop for expressly this purpose. It allows us to do all sorts of passing around, as it were, of this stuff without ever corrupting the color because we never introduced the device part of it. However, then, for me to look at this file information on my monitor, I need to push it through a profile, just like we did on the board back there, to remove the device dependency of this monitor, to correct for whatever deficiencies exist in this monitor. Does that make sense? And each and every one of you, if I shot that file out to all of you guys, as long as you have the correct profile for your monitor, all of us would have the exact same color. We would all be looking at the exact same scene. Does that make sense? And then finally, if I go out to a printer, I do printer profiles as well. And in the printer profiling part, there's more variables than just the printer. In the printer profile part, the other variables that you have got, and these are really critical, is you've got the printer itself. So even though there's a whole ton of P800s out there, you cannot do a profile for one of them and use it on another one. You've got to do exactly the printer that you want. And people look at me and say, Jesus, Verser, how fucking anal can you be? And I say to them, how many people in this room have perfect color? When they look at their monitor, I do one print, it goes up there, it's exactly what I want, and I leave. I don't do test strip. They asked me once, I was doing a mural print here, and they said, would you like a test strip? And I said, for what? And they go, well, to make sure your color's okay. And I was like, I expect my color to be okay. And they were like, no, they can't, no. And it was perfect. At any rate. About your printer. The printer itself is the first variable that you've got to take into consideration. The paper is a second variable that you have to take into consideration. So if you build a profile for a glossy paper, it's not going to be the same as a matte paper. Epson's glossy is not going to be the same as Red River's glossy. So it's all very specific individual paper. The ink that you're using, the ink set, so there are different profiles if you're using a black matte ink or a photo black ink. It's different if you actually put in third-party ink. So if you have a printer and you take your printer cartridges to Costco and you refill them because you're going to save $5, the profile has to be made for the Costco ink, not for the Epson ink that you got your printer originally with. Does that make sense? And then finally, we talk about the media setting, and we'll look at media setting in just a second because I'm actually going to do a profile for this. Those are the 4 things that you actually need to build into a profile for a printer. But once you do this system, your color will be completely fluid, predictable, change your life, and give you a whole lot of extra time I see people do test strip after test strip after test strip, and I'm just like, shoot me now. I would much rather go home at 8 o'clock. I hate working at night, except for teaching you guys. Yeah, sure. Okay, is this making sense to everybody? Okay, we need to look at one other thing about color, and then we're actually going to build one of these printer profiles because, like I said, I'm going to lose that guy first. So the last thing that I want to talk about this really quickly is, because this part matters, I want to show you guys something that I haven't shown in a really long time because that's how good you guys are. This is the much longer color lecture that you're thrilled you're not sitting through. Okay. How many people in this room have ever heard the term LAB, describing color? Okay, remember your color wheel. I'm not the color wheel, but the color. The color sync utility. I need everybody to go there again really quick for me. Remember this guy right here? This is actually built on an LAB system, the display of this. You see this little plot right up here? It says an LAB plot. Don't let that like confuse you or get you too nervous as far as that goes, because I'm going to show you. This is an RGB plot right here. This is the color wheel again. Let me show you the color wheel that I was showing you earlier, not this one. So sorry, hang on. So this color wheel right here, remember we saw this guy? So this is a color wheel that's got three primary axes on it. It's got this blue, yellow, this green, magenta, and then this red cyan. You don't have to do it using those. You can actually use it only doing a coordinate of 2. And what they do in an LAB model is they keep the blue, yellow one pretty well, and then they draw a line down here that is exactly halfway between this yellow line. So they can describe color in here only using 2 coordinates as opposed to 3 coordinates. Does that make sense? And it looks like this. Well, again, I'm going to flip this one. The one I'm going to show you is the one that's been flipped on its side. And it looks like this. You end up, they call this a green-red axis right here. The blue-yellow is actually very close. They do this green-red. Some people will call this a green-magenta. And then you've got, again, white that's up here at the top, black that's here at the bottom. And so this is what you're really looking at when you're in that color sync utility, is this model right here. Does this sort of make sense? And the reason this is important to make sense is that this is also how you color correct in Camera Raw. Is this right here. You don't have RGB. You do have RGB curves in Camera Raw, but in the beginning part, you deal with color temperature and tint, don't you? So I need you to keep that in mind. So if we look at the file, if we go back to your Photoshop, you should still have that Bruce Fraser file in Photoshop. Do you still have the castle on? Let me cancel this. If you actually close the castle up, because I didn't open this as a smart object, and simply go up to the file menu, open recent, and open it a second time, it'll bring it into Camera Raw. This slider right up here, temperature and tint, this is the LAB model right here. The B part of an LAB model is the blue to yellow, and the axis of an LAB model is this tint. It goes from green to magenta. So the system that we deal with in color here to begin with is an LAB system. It's not an RGB system. We're not dealing with RGB, not until we get into Photoshop, really. Does this make sense, everyone? So we need to talk about temperature. What is temperature? What is color temperature? Anybody? Well, it's basically this scale that's going from blue to yellow. So it looks like this. This is the color temperature scale, and the way they built this whole thing, there was a guy called Kelvin. How many people here in this room have ever heard of degrees Kelvin? You'll hear it all the time, right? Oh, that light is the 3200 degrees Kelvin. Well, the way this whole thing, the whole temperature part started is, imagine a glass of water. Inside a glass of water, there's little molecules, little particles of water, and they move. And the more energy you put into that glass of water by heating them up, the faster they move. And eventually they become steam and they completely escape the glass. The opposite side of that is that you can cool them down and the molecules get slower and slower and slower. And as they get slower and slower and slower, you start to move towards ice. You're taking energy out. Well, that's a finite system. That can't happen forever. At a certain stage of the game, you remove all the energy. There is no energy in it anymore. And all the molecules are frozen. They don't move, not frozen like ice. They don't move anymore. They have no energy. They don't move anymore. That's a finite place. It happens at about minus 276 degrees Celsius. It can't get any colder than that because you've removed all of the energy. In Kelvin's world, that's 0 degrees Kelvin. He decided he wanted to name the scale after him. I don't blame him. I would do the same thing. So it's where 0 degrees Kelvin is where there is no energy in it. You can also not have anything that's blacker. It is the blackest thing that exists because there is no energy. There's nothing coming out of it. There is no emission. It is as black can be. Then you can start warming that thing up. They call that thing a black body. You start to warm it up. And when you get to about 2000 degrees Kelvin, it starts to glow. And we all know this. It's like a light bulb. You start to put energy into a light bulb, and it starts to glow. As you continue to put energy in it, that light actually changes color. And as you start to put more and more energy into it, it starts leaving this yellow range. And by the time you get up to around 9,000, 10,000 degrees Kelvin, you're actually into a very, very, very blue light. Does that make sense? So you can describe this color based on degrees Kelvin. And that's what happens. Somewhere right here in the middle, right about 6,500 degrees Kelvin, the blue offsets the yellow. They cancel one another out, and you end up with a neutral color. That is why we always deal with white points, neutral white points of 6,500 degrees Kelvin. How many people in this room have ever calibrated a monitor? When you calibrated it, it asked you to set the degrees Kelvin for the white point. What you're saying is that I don't want this monitor to have this cast. I want it to have no cast at all. So it's the color. Does this make sense, everybody? What is neutral? Is neutral warm? Is it cool? Or is it right in the middle? So in photography, incandescent lights are around 2,800 degrees Kelvin. If you go to the studio and get one of those hot lights there, it's around 3,400 degrees Kelvin. If you get a strobe light, what color temperature is a strobe light? It's 5,500 degrees Kelvin. If you go to the top of Mount Everest and you're shooting available light, it's actually around 1,300 degrees Kelvin. It gets incredibly blue. Top of Mount Everest on a sunny day with no clouds in the sky, bright blue day at noon. That's how blue that gets. So it's color. Does that make sense? Okay, so you need to remember that part. That's the last part of this we're going to talk about. However, we are going to go back to this part right now, and we are going to build one of these. So what I'm going to start with is the printer profile. Typically, I would start the other way and move forward, but we're going to do the printer profile. Can I get somebody to go back there and turn on all the lights for me, please? And then I need everybody to stand up and come over here, because you will also not see this on the video, because, again, this is a demo like in real time, and I don't have anything that'll show this. I will show you the software that exists for this on the demo part, but... Great, thanks. So you can get comfortable. You can drag a chair over just as long as you can see this whole setup is where I'm trying to get you to. All right, so this is the granddaddy of them all. This is actually made by i1. This is who makes the color calibrator that we're going to use. This is also who makes the software to do the camera profiles that we're going to do. So what I'm trying to do right now is build one of these guys right here. Does that make sense to you guys? Okay, so to do that, you can't take this home, but you can check these out. You can print the targets that you'll use for these at your house. So if you've got a printer at your house that you want to build a profile for, just print the targets out, bring it in here. You can check this out when you're here, measure it. It takes 10 minutes, build your profile, take your profile home, plug it in, and your life will be great. Make sense? I'm going to show you right now, so hold that thought. Okay, so we'll start with the software part because that will answer your question, but I've got to plug this in. And this is the one thing you should know about all of these systems. When you use these things before you start the software, plug the hardware in. So remember, we were talking about here, we were saying the way this stuff works, it's a software-hardware combination. The software is going to spit out colors that it thinks, that it knows. This thing, this is a spectrometer, it's going to measure those colors, and the software then can measure how far off was the color that was asked for and what the printer gave me. Does that make sense? Again, exactly like we're talking about up there. Are we good on this? So, but anyway, you want to plug this thing in before you fire the software up. The software for this comes, they have it here. They don't have a version of it in here. They do have it in this, and we will talk about this. This is a monitor profiler here. So it all uses the exact same software, so you'll see the software again. At any rate, it's called i1 Profiler. And I'll talk about how to find it later if you guys, if you can't get to this part right here. But anyway, you want this plugged in first. You go to the application folder. It is called i1. You double click on i1 Profiler. It launches this thing. And this screen will come up. If it gives you this information, I typically always do install the updates. We don't have time to do it right now, though, so it won't appear to be any different to you guys. But if I were you, I would go ahead and go ahead and install the update. They refine this stuff all the time, but I'll just say remind me later. You can profile all of these possibilities. You can do a display profile, which would be monitor profiling, a projector, so I could do that guy if I wanted to, a printer profile, or a scanner. So whatever it is you're going to profile is what you need to actually have pick right here. So I'm going to pick the printer profile because that's what we're going to actually do. When this actually happens, it's going to actually walk you through the whole steps of this. It gives you a help thing on this side over here, and it gives you options on this side over here. Now, this becomes the sort of tricky part right here. In this drop-down menu, you've got to select the printer that you want to profile. So you click and you look at my drop-down menu right here. I've got a series of possible printers to profile. These printers exist because I've installed the drivers on my system. So if you don't have if you don't have the driver for a printer installed in your system, you've got to install it. The easiest way to do that is to plug the printer in. So if you wanted to do this for one of those printers out there, on your laptop, you would simply plug the printer into your computer. You would come up to the Apple menu. You would come down to System Preferences. You would click on Printers and Scanners. You would click on this plus button, and it will show up in this screen right here. You simply click on the printer and say Add. When you do that, that printer will show up in this list right here. Does that make sense? If you're not connected to the printer, you can actually do a search for the driver. So for instance, we don't have time. I'll show that to you when we get back because I got to make sure I get through this because I'm going to lose this guy in about 20 minutes. You can do a search for the driver software online, download the installer package, install it onto your computer, and it will show up in this guy right here. If you've already turned the software on, you probably have to restart the software if you've loaded a driver because it's looking at what got loaded when you launched it. You don't have to restart your computer though. Are we good on this so far?
Is it based on like if you're like Wi-Fi, like it'll find the printer if you're nearby?
If you're connected to the printer at all. If it can see the printer, if it can see the printer, it will download the software. The irony of it is that most printer softwares, most all of them, are already on your computer. It's just a question of activating them. So it was one of the things that Apple did when they decided they didn't care how much hard disk space they ate. Do you know my very first Macintosh? I could get a system and an Excel spreadsheet and 128K of memory. That's an eighth of a megabyte. Yeah. So at any rate, when you get this part up, I'm going to do this for an Epson 4900 because that's what I use to actually print this target out. It's going to say, what size target do you want to actually print? Do you want to do a small, a medium, or a large? This is what the target looks like. This is a medium one that's actually right here. This is basically what they look like. They're colors. They're just color swatches that are printed out. So when you pick these things, that'll actually then, you'll say, you use this software to do the printing. It will turn off all the color correction. It will give you a raw, generic version of what your printer thinks it should be doing. And it looks like this. This is the small target. This is 400 patches. If you go to the medium target, like the one I've got right here, it's 800 patches. And if you go to the large target, it's 1,600 patches. Depending on the paper size that you use, and the paper size is right here, it will either print all of this on one, or it'll break it up. And so you can see here in this one, it'll print, the 400 will print on a single 8x10. But if you go to an 800, it has to do it on two patches, on 2 targets. So it'll do it on 2 targets, but it'll say right here, this is the 800 patch chart. This is page 1 of 2. This is page 2 of 2. So you'll measure this one first, and then you measure this guy. It's simple. If you've got Super B 13x19 paper, you can get a 16. You can get the largest of the targets printed out on a single piece of paper. Are we good on this part? Okay. There's a cradle that comes with this guy that's critical because inside this cradle, if you drop this down, is the calibration target for the spectrometer, which you need to use. Everything is calibrated. This is a device. We need to eliminate the device dependence, and that's what this little white patch does. Make sense? So we're just doing the same thing all the way down the line. So I'm going to go ahead, in this case, say that I did a small target. It's this one because it's going to do the software stuff for you, and it's going to say, okay, give me next page, give me the next page, give me the next page. I'm going to say, okay, okay. So at any rate, I'm going to go ahead and you would click print right now. The targets print out. You would let this dry for at least an hour if you can, but I've measured these things after they just came out of the printer. But letting them dry will help you a little bit. But nonetheless, you click next, and it's going to tell you what to do, and it's going to say, you've got to calibrate this target. So you open this up, and this thing sits in it. So this is where that little thing right there is what reads this stuff. It sits in there like that, and I'm going to just click on the thing that says calibrate. It starts to actually do its thing. And it says, okay, you need to set this thing up so that we can actually measure this guy. And I'm going to say, okay. There is an easel in here that is designed to make measuring these things extremely fast. The original versions of these that I had, you had to measure every single patch one at a time. You had to locate this on a patch, click and wait for like 10 seconds for it to measure, and then line it up on the next one. A 1600 patch would take you 2 or 3 hours to actually do. You can do it in less than 10 minutes now. So this is critical how you set this guy up. So this is designed to take that 13x19 piece of Super B paper. This is actually smaller than that. This is only an 8x10 piece or 8.5x11 piece of paper. So when you load it in this is a clipboard that just holds the target. When you load it in this, you need to center it. And you can do it by eye. You don't need to get out a ruler and measure this. But you need to center this. If you have this kicked over to one side or the other side, it will not work. So if you're doing these smaller sheets of paper, you need to get this guy in the center like this. Then this thing is a ruler. There's a clear side on one side to help you line it up. And there's this slider rail on the back side of this. The teeth of this slider rail fit into the base of this guy. And this is what allows you to do your control on this really quickly. So the way this works is you set up the ruler to measure the first row of patches. So the first row is what's revealed. You'll see that these rows are numbered. So I'm going to set this up so that it reveals row number 1. Does that make sense, everybody? And then the cleats here fit into those 2 holes right there. And if you do this correctly, it will line this guy up so that the sensor is directly over row number 1. Are we good on that part? Okay, so I've got this part right here, and it says, please make sure that the target's dry, use the clip to hold it down, center the top row, blah, blah, blah. It goes through all of this stuff for you. However, in doing this part right here, you can set this up as well. You can forget the top one. You would never, this is for spot color. It's a printer thing, something you guys would never do. But a single scan basically means we're just going to measure these colors going in one direction. A dual scan means we're going to measure in two directions. It means you measure row 1 going left to right, and then row 1 again going, I just said left to right, right to left. So it's just a more precise way of doing it. Again, a double scan on the largest target will take you about 10 minutes to measure it, so it's worth doing. It makes for a more precise profile. But we don't have time here, so we're doing it on this version. We good on this? So I'm going to set this to single, and it's probably going to ask me to calibrate again. So again, I'm going to set it back here and hit calibrate again. It's weird that they do the software like this, that they don't let you pick that part first. But then again, it's going to say, okay, we're ready to go. So I'm going to get this part on here. You want to start all the way to one side. It does not matter which direction you measure in. The software will know. So you can start, I can start on this side, I'm going to pull it this way, or I can start, that part really doesn't matter. To actually make this thing work, there's two little buttons that are right on the side here. So when you hold this in your hand, you squeeze those buttons. What's really critical in doing this is you need to turn the sound of your computer up, because this thing needs to charge before you actually measure a row. So when I squeeze those things, you're going to hear this little bell go dink, and that's saying it's ready to measure the row. If you go before that, you will get an error warning. I'll show you what it actually looks like. So again, the software is really smart, so it's pretty hard to screw this up. So at any rate, I'm going to squeeze these things together. You hear the little dink, and then you just drag across and let go. If you get the two green lights that just showed up, you know you're good to go. And also, it will actually, the animation will drop down and say, we need to do the second row. So I'm going to do the second row. Again, click. Wait for the dink. Both of them work. Click. So you get what's going on here. Measuring the patches that should be known colors. This is what my printer gave me. This thing is saying, okay, well, that's not quite right. You get where this is going, right? I'm going to go to the next one down and show you what I mean by the errors in here. I'm going to click and go fast before I get the okay to do this. Red lights are blinking there. You hear this warning, blink, 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 blink. And if you look at the error message, it's going to say the scan was started before the lamp was ready. Do it again. It's really hard to fuck this up. All right, so I'm going to click again. Wait for the beep and come across. The next thing you can do is actually make a mistake and go to another row entirely. So I'm going to click and go to a completely different row. And it gets this warning, and it says it's an incomplete measurement. It's saying, it doesn't know what row I measured, but it knows the one I need to measure. And it's telling me that I need to go back to row number 5. So again, these are numbered. So I'm simply going to go back up to row number 5 and click and drag. And see what this warning is. Incomplete. Please do it at a slower pace. So again, I drug across the line too quick. So it's not, the lamp was ready, but I went too fast. So click. And we're going to get through the rest of this. So you can have these done professionally. They charge about $150 to do this. So the enterprising young Columbia College student who wanted to pay down those student loans would consider a career in profile making. If I can do $150 in 10 minutes in a single hour, I can do, that's $900. Who in this room would work for $900 an hour? Just saying. In your spare time, right? All right, so that's it. It's gotten through it says the measurement was completely successful. Double click on the patch to view the patch data right here. So I'm simply going to hit next on this guy. Actually, I'm going to go back and take a look at this. Oh, anyway, can you guys see this? These are now the before and after colors. The color on the top was the one it expected. The one on the bottom was the one that was measured. How on earth? Look at this difference. It's not, you're guessing at this stuff. Without the profile to actually get rid of the device dependence, you never had a chance to get a print that worked. You never had one. And now at best, you're sort of getting one kind of close doing all the iterations that you're doing. This is just a nightmare. Make sense? Okay, so I'm going to go ahead and hit next on this. You do not need to change this. This is just about the illumination of the print that you would actually be viewing it in. You will notice in this drop-down menu right here, though, that there's a D50 right here. That's a color temperature, 5,000 degrees Kelvin. That D65 is also 6,500 degrees Kelvin. Again, a more definition of neutral white. The A's and the F's that you actually see right there are fluorescent lightings. But again, you would simply leave this. You don't need to make this profile specific as far as that. Light specific is what I'm talking about right here. So I'm going to just simply hit next. And it's going to say, okay, you want to create and save the profile. And I do. However, to say the 400 patches is meaningless, that means absolutely nothing to me. By the way, close this target back up when you're not using it, just to try to protect that part. What this patch is this is a Canson Infinity Photosatin Premium RC paper. It was printed on an Epson 4900 using the PLPP, which stands for professional. We'll look at it here, but it's a presentation matte paper. That's what it actually is printed in, using a matte ink. That's what this is. So that's the name I have got to give to this profile. So what I'm going to call this thing is, I'm going to start with the 4900 because I know that that's what it is. 4900 underscore CAN. And what did I say this was? This was a Photosatin Premium. So PHOSAT RC. Underscore, and then I said, oh, my setting on this was PLPP. I think that's a PLPP, right? Ultra Premium Presentation Matte. That's what I did on this. So it's a UPPM. That's what it would be. UPPM underscore. And then I would put your initials in there so that you're not making any mistake between this printer profile and somebody else who made one as well. Does that make sense? And I'm going to go ahead and hit create and save this profile.
Would this be something that could change? Like, I mean, over time?
Yes. Okay, no, that's a great question. That's a great question. It used to be that people would say anytime you actually trade the inks out on your printer, you have to do a new profile. Printer inks have gotten much, much, much more standardized now. They do them in such vast quantities that you don't get into that drift anymore. But I would say, for me, anytime I go in for a serious printing session, I will generate a new profile. If it's been a week, I won't. But if it's been 6 months since I've really printed, I do big print portfolio things, whatever, I'll just generate a new profile. It may be the same identical inks. I don't care. It takes me 10 minutes and then I don't screw with it. Paper stock is the same way, though. If you buy a paper stock that's, this version of this paper has been sitting around for, 2 years, and I buy another set of it, the stock itself has changed as well, so I would do a different profile for both of those respective batches of paper. But things have gotten shockingly consistent in this day and age, so that would be what I would do. Okay, so it's built the profile for me. So I'm going to say that this would be a good time to take a break. So I've got, let's call this 5 minutes of 8. What we'll do is when you get back, I'm going to show you the second half of this. But this lets me get rid of this guy because you should know this right now. The digital desk right there is closing at 8 o'clock. They're going to lock us into this room. No, not lock us in, but we're going to be here. Don't tell anyone. Make sense? So somebody's got to stay in here to let everybody else in. They're going to close that door. So if you need to, bang on the door that's by the print place right there if you got locked out, okay? Because they're going to close the gate. We good? All right, I'll see you guys. So anyway, if you could be back at 10 after, that'd be great.